Lecture 6, Module 1, DMAIC Analyze Stage 2, Analyzing the Process. In this module, we'll cover process mapping, SIPOC, value stream mapping, time value maps, and spaghetti diagrams. Remember process rule number 1? No process without measurements. And process rule number 2? No measurement without analysis. Now, process analysis and data analysis. The analyze phase actually has two separate areas of focus. Analysis of the process that was being measured. This analysis will typically look at measures concerned with how the process is being run. The lean measures discussed in Lecture 1 are normally the focus here. These mostly can involve critical to schedule and critical to cost measures. Then there's the analysis of the data that was measured. This analysis will focus on data generated by the process or measured from the process in some way. Most often these are critical to quality measures. For instance, how much product did we make and how much of it was defective. The process stage of analysis also consists of two parts. The first part utilizes tools to map the process to learn how it really works. What exactly are the steps in the process? Where exactly do these steps take place? And how long do they take? The second part utilizes tools to evaluate the process and identify what can go wrong in the process, and where would these things go wrong, and finally, what causes these problems. The first part of the process analysis is meant to truly understand how a process works, and involves looking at each step very closely. In this first part, some of the tools that Lean Six Sigma discussed in Lecture 1 are used, such as process mapping, value stream mapping, time value maps, and spaghetti diagrams. In this first part of the process analysis, the process should be examined, keeping in mind opportunities to employ Lean or Six Sigma techniques wherever you might find the opportunity. And the process maps and value stream analyses can reveal these places that could benefit from these techniques that are not obvious at first glance. Special note here, although it is important to use the previous stated tools in your analysis, it is even more important to go out and, as we say, walk the process and see what actually happens during the process. Want to really understand the process? Do it. This simple exercise will give you insights that these mapping tools cannot completely reveal by performing them sitting in a conference room or at your desk. Go out and walk the process. A process map illustrates the individual steps of a process using connected symbols. The symbols are linked in sequence and show items such as the inputs and outputs, what decisions are made and the choices for those decisions, what data gets generated, and the kind of documentation that's generated. This process mapping can identify non-value added steps. It can also reveal problems such as process bottlenecks where things are getting clogged up. And it obviously will identify opportunities for improvement later on. A time value map lays out the activities from a value stream map or a process map and then separates them individually into one of three possible classes. Value add activities. These increase the value of the product or service from a business perspective. Either the customer is benefiting or it's a regulatory benefit. And these are usually marked as green, labeled as green. Business non-value add activities. These are steps that are necessary, for instance, of regulatory, or something that's required by regulatory, but do not increase the value of the product or the service. And these are generally shaded as gray. And then non-value add activities. These are steps that add no value whatsoever and are not required by the business in any way, either regulatory or by the customer. And below is an example of a time value map. Note that the color of the business non-value add in this example is orange. So as you see in the very beginning, in day 1, there are a lot of essential non-value added time. This may be filling out paperwork and things like that. And then non-value added time whatsoever, waiting around for things. At the beginning of day 2, we have some value added, and then a long period of time where non-value added time is being spent. Then again, a short period of value added time, and then a long period of essential non-value added time. This may be batch release, filling out batch records, batch record review, things like that that are required by regulatory, and then really add no value to the product from a customer perspective, but do add it from a regulatory perspective. And then finally, there's another short period of value added time where the product is being delivered to the customer, perhaps. SIPOC. suppliers' inputs, the process, outputs, and customers is a tool that can be used to help identify these processes in an organization. SIPOC is a form of a process map that connects all suppliers and their inputs to the processes and then subsequently to the outputs and the customers that receive them. So any opportunities for improvement can be identified. Note it's important to be aware that an improvement in one process that you may come across may create problems in another process. So the looking at the entire process is very important, not just at one place where an error may be made and making a change there that impacts other parts of the process. The SIPOC combined with the fishbone, which is the cause and effect diagram, will allow users to study the relationships between the inputs and outputs quite visually. Inputs and outputs. Every process is comprised of steps that have inputs and outputs, quite distilled. All of these inputs and outputs can be measured and evaluated as to their effect on the process. Here we see a very simple, distilled down view of a process with a single input and a single output. And all processes have inputs, usually described as X subscript N, as there may be several types of inputs, quite a few going into a process. And then all processes have outputs, and these are described as Y subscript N. There may be more than one type of output for a process. And finally, the process can be described mathematically as Y is a function of the number of X's that are coming into the process. Now there are 6 types of inputs, X to the N, to a process that are called the 6 M's, and this is a methodology that is found in ICH Q8 on process development. So obviously it should be paid attention to in the pharmaceutical industry. These M's are methods, the machines, manpower, materials, measurements, and Mother Nature. Now the methods could be described as your SOPs, the machines, the equipment that you use for manufacturing. Manpower obviously is the labor pool that you're using. Materials would include your raw materials or work in process. And measurements would be the actual measurements you take on these raw materials and work in progress and finished product. And then, of course, Mother Nature has her way of affecting maybe temperature and pressure, humidity, relative humidity, and all along the way in this process. Now, this can be graphically pulled together as a diagram such as this, showing how all the variability from these different areas, machines, methods, measurement systems, all have a final impact on the output of the process. Now, it's important to point out that this is in the footnote there is from Understanding Key Terms for Modern Quality Assessment, a presentation given by John E. Simmons, a PhD, from CDER of the Food and Drug Administration. So it's quite clear that the Food and Drug Administration, the FDA, is very much aware that the variability of all of our inputs to our processes have an effect on the output to the overall system, meaning the output of the quality of the finished product, and hence an effect on the patients. So they're very keenly interested in this, and they're very well aware that all these inputs affect the overall process output, and hence the quality of presented to the finished to the patient in the finished product. Now, Ishikawa diagrams can be used to map a process. Here we see an output, whatever it may be, and we can follow a process all along, looking at the inputs from input 1, 2, 3, and input 4, and how each one of those inputs affects the final output of that process. There are many inputs and outputs to a manufacturing operation. The output of each process becomes the input to another process, and every process is dependent on the input from several other processes. All these 6 M's we've talked about. All inputs and outputs of a particular process should be measurable so that they can be determined and controlled. And below we see a blending, feeding into granulation, feeding into drying, feeding into compression. So some of the inputs into the blending process may be the raw materials themselves. So let's say lactose, max stearate, the API, and they go into the blending process, and the output is now the final blend, pre-blend or final blend. That blend now becomes the input into the granulation step. So the inputs into the granulation are the blend, the granulating solution, perhaps the rate of addition of the granulating solution, for the RPM of the mixer. All these are inputs into that process, and finally coming out is the granulation on the other side, and some of that may be described by its moisture content and things like that. Those are now inputs into the drying process. So the load of moisture going into the drying process, and that may be a fluid bed dryer or just simple oven dryers. And the output from that would be the finished dried granulation, which now has a certain moisture content. And that now is an input going into the compression area. So varying moisture content in that final granulation has an effect on the process of compression, and that may impact, for instance, the output in terms of hardness and dissolution. So as you see, all the steps along the way have an impact on the final product. A value stream map is a flow diagram documenting every step of a process. A value stream map is a lean tool used to identify waste and help reduce process cycle times. The value stream map describes a series of steps that a manufacturer takes to produce and deliver a product, and there are three main parts. One is the flow of materials, the movement of raw materials, the components, work in progress, and finally the finished product. The other is the transformation of materials, the conversion of raw materials, components, WIP into the finished product, or raw materials and their components into WIP at various stages. And then flow of information, and this is the movement of information required to receive, process, and release raw materials, components, WIP, and finished products. So, for instance, the purchase order that comes in for the to make a certain number of tablets or batches, the batch records that are started, the investigation reports if there are errors, release of raw materials, analytical reports on batch release, etc., etc. There are many pieces of information that are generated concerning the processing of that batch. Now, value stream mapping is defined as the simple process of directly observing the flows of information and materials as they now occur. This process allows companies to map the flow of products from raw materials entering the facility all the way through each of the manufacturing pharmaceutical steps to the distribution department or shipping or warehousing, whatever it's called, as the final finished product. Now, the mapping process begins with analyzing the current state of both material and information flow. This visual flow is then examined for any non-value-added steps, and from there a future state map is created as a guide to the desired future state of the process. A spaghetti diagram is a map of a work process showing the actual flow of work and distances traveled during the execution of the task. Work that has not been thoughtfully planned or typically without little thought to efficiency, so the map takes on the appearance of a pile of spaghetti. Processes whose maps look like spaghetti are definitely inefficient time wasters and are often prone to safety issues. And as we see here, we have a number of steps that go back and forth and cross over each other. So step 1 moves over to step 2, jumps up to step 3, goes across the hall to step 4, then comes back to step 5, etc., etc. It may be more functionally efficient to move steps 1, 2, 3, and 4 maybe over to the right and have all those steps done very close to each other, so it's very easy for those inputs and outputs to flow between each other, and then maybe moving over to the left for 4, 5, 6, 7, and 8. That may be a better layout, or it can be broken up into something else, but not a lot of crossover, because crossing over allows for safety issues, as already said, but also allows for the introduction of cross-contamination.